Okay. All right. Hopefully they can hear me. I think I see like the mic going green, so it'll probably be fine. Okay. So welcome to our last lecture of the quarter. A couple announcements before we begin. We're gonna do that like sort of like work session where you guys can finish anything that you need to if you still need us. That'll be this Sunday, 1 to 4 p.m. IEEE lab. We won't really have any food and I don't know. It's kind of sad, but yeah, you can show up, do any lab you want, that sort of stuff. The other thing is after this lecture is over, I know some of you guys have expressed some interest at being an officer. If you've read the sort of interview format that we posted, or if you haven't and you want to read it and have us available, or me available, I suppose, to answer any questions you guys have about that document or anything else, we can like sort of sit and have a chat. Hopefully it won't be too long because we're gonna stretch into dinner time there. But yeah. Okay. So this is our sixth and like last lecture of the quarter. It'll be on a bunch of miscellaneous stuff that we haven't really covered yet, but you guys have sort of seen some parts of it in lab 5, but we probably told you things like just use this and it'll be okay, and then we were going to explain it here. So that's what this lecture is going to be. So hey, come on now. Okay, all right. Let's talk about overfitting for a second. So we've probably like sort of mentioned this to you guys, or you guys have learned about it by yourselves for some time now, but let's just formally define the problem because we're going to talk about a lot of ways you can sort of combat overfitting in today's lecture. So a lot of machine learning is sort of like techniques in machine learning are motivated around like combating overfitting, because overfitting is typically something where like, you train a model on some data, right? That's what you always do. But then you adhere to the training data too strictly, and then your validation accuracy suffers for it, or your test accuracy suffers for it. So we usually try to combat this because, we want our networks and stuff like that to be generalizable. So something like that we sort of intuitively discuss when we're doing linear regression is like we sort of talk about model complexity being correlated with overfitting. So like the more complex your model is, in this case we have like I don't know, like ninth degree polynomial or something like that, fitting something that what we can kind of generalize as humans to be linear. But when we do overfitting in this case, it passes through every data point. The train error is very low, but this will do a very bad job at generalizing like a new point that appears like somewhere in the top right or something like that. So yeah. So this is something that you guys have probably seen already as well, but again, we're just going to formally go through it. It's called ridge regression, and basically what it is it's a penalty applied to the size of your weights. So essentially, when your model becomes complex, one sign that you can sort of tell your model is becoming complex is when your weights are large. So like intuitive way to describe it is like if we have like some ninth degree polynomial term or something like that, if the term in front of like x to the ninth is 0, then it's not a ninth degree polynomial. It's actually an eighth degree polynomial. And if we sort of like take that and say like, okay, let's reduce the weights as much as we can to try to penalize the model for having big weights, then we won't really have as complex of a model because the weights will be reduced like in front of the polynomial terms, especially the higher order ones. So this is like applicable to neural networks as well, but this is the simple case where we're just talking about polynomials. So basically, when we look at this like model that fits this line, we can say that the weights exist for the polynomial terms that are higher. Like clearly this is a ninth degree polynomial, so we know that the weights have like some, finite values that are not like really close to 0. So yeah, basically this line is like changes so frequently or changes so rapidly because of those large weights. If we were to penalize those weights, by using ridge regression, we'd get a model that looks like this. Now, this obviously looks better, more generalizable. And even though like the more clean solution would probably just to be don't use like a ninth order polynomial to like approximate what is probably going to be a line, this is still a good way to combat overfitting. So how do we go about doing this? Well, this is probably something you guys have seen before, but we basically say that we apply a penalty to our weights for being large in our loss function. That way, when we minimize our loss function, we also minimize the size of our weights. So this is mean squared error. I don't know if you remember this from the first machine learning lecture we have, but if we just simply add a term, where we add this lambda, which is like a regularization hyperparameter. It's something we pick, and then we sum across all the weights squared to make sure that they're all positive, so they don't sum destructively. If we do that, this is basically saying our loss is going to be big if our weights are going to be big. So we just penalize them. This is like a pretty intuitive solution to this question. So any questions about this? Okay. All right. So you can pick lambda, like I was saying, it's a hyperparameter. And yeah, so since larger weights increase the loss, we're going to converge to something that has smaller weights in our gradient descent. So that'll sort of combat our issue there. Here is like an example that we sort of concocted with like implementing L2 regularization. This is you can see that like the orange line would do a much better job generalizing if we continued to generate data from the same distribution. So yeah, this is like generally speaking a good thing to do. Okay, let's talk about dropout for a second. So dropout is something that you guys have probably seen in lab 5 already when you were exploring like all the models you could add to Keras. If you haven't, it's fine. It's like a pretty simple idea basically. So dropout is like a way of like ensembling. So if you guys aren't familiar or haven't had M146, what ensembling is basically saying, okay, if I have a model that's like sort of bad, right? I might like enhance my model by having another model next to it. And if I sort of combine the two results from those models and like average them or combine them in some way that both of their inputs somewhat contribute, in theory, like I'm more accurate because my models, if they're truly independent, like my models are independent from one another, they won't make the same mistake on the same data. So if I have like 5 models and one of them makes a mistake, if I only had that one model, that data point would be misclassified. But if I had 5 models and one of them made a mistake and 4 others didn't make a mistake, and I ensembled them together, we'd theoretically get a better result. Now, that sounds really good. So you might be like, why don't we just train 1 million models and put them side by side? But that's like computationally expensive. And also not every model you train is entirely independent because you're training it on the same data. So let's apply this to neural networks for a second. So here we see like some neural networks, right? And you can see like, ignore our like, I don't know, artwork. You can see that these models sort of have different architectures, right? So these would count as different models. And we'd be like, oh, let's try to ensemble these to create like a more efficient model like altogether. So what we can do in neural networks is instead of training 3 different networks of these architectures, we can choose certain neurons to drop out, and that'll effectively be another network. Because if I have like, I think we have something showcasing this. Yeah, so this is basically what I was reiterating. We want to train multiple models with slightly different architectures, so they're different models, and then we will take a majority vote of what all those models predict. That's called ensembling. So this is computationally expensive. So we can consider something called dropout, which is basically this. If you noticed, those like different shapes, they weren't actually fundamentally different. They were usually just missing 1 neuron from the connection. So here we sort of visualize that. If we sort of say, okay, like we can consider dropping out some of these neurons as we're training our model, we can train different models effectively. Like it's sort of like we're training a different model, but in reality, it's the same network. We're just choosing to drop out certain neurons. You can sort of think of it like saying, we don't want our model to become overly reliant on like certain neurons. So having a probability to drop out neurons at like some given point in training with like a certain probability that we decide that's a hyperparameter, that might help combat overfitting as well. So dropout is like empirically shown to be pretty good. It's typically worth the computation time that the slide is sort of talking about because it's also not super computationally expensive. Sorry. But in terms of implementation, like what happens is during the training time, we do these neurons, we drop them out and stuff like that. But when we actually test, in order to ensemble like all of the different like quote unquote models that we've trained, because we were effectively training different models at every training iteration run, because we were dropping out different neurons at every iteration. We like when we do finally like the test, like we run an inference with the model, we'll include all those models, or we'll include all the neurons again. They just have to be normalized by the probabilities that you drop them out with. Mathematically, like if that doesn't make sense, like don't worry about it too much. But it's a way of ensembling all the model like votes, I suppose, together. Hey, any questions about that? Okay. All right. Another way we can combat overfitting. So overfitting is like the process of fitting too rigorously to a training data set, right? Now that's only a problem if your training data set isn't representative of like all the data in the world. So if we were like data collection masters, we could just collect all the data in the world, and it doesn't matter if we overfit like entirely to the training data. If the training data is all the data you could possibly see, then you don't really have to worry about overfitting. So in general, when you train a model, it's a good idea to have more data. Did that logic like make sense? Okay, so one way we can get more data is data augmentation. So let's say we were training on like these mice here. All right. If we only have these two images of mice, we can imagine that like if we were asked to like classify the difference between this mouse and this mouse, if these were the only data points we had for our neural network, it probably wouldn't train very well because, you know, if we presented it some new training data set, like a mouse can look totally different, and so can a computer mouse. So we might want to consider generating more training data. So what if we were to use the same images more times, but not like fundamentally change them? This is the process of data augmentation. So, all right. Basically, this is what I was saying earlier, which is like neural networks will find patterns to minimize loss in the training data. So if we just expand our training data to be more comprehensive, we're in theory doing a better thing for our model's generalizability. So what parts of this image, right, don't actually contribute anything to the fact that this is like a mouse, right? Like we have some empty black space here and stuff like that, right? This mouse doesn't have to be at this particular pixel position in the image. It doesn't necessarily have to be like black and white. It doesn't necessarily have to be a lot of things. So we might ask ourselves, you know, why are we restricting ourselves to only thinking of this image in this certain way? So here's some examples, right? So what we can do with our original data is we can generate, say, like 5 different points from it. And we can say, okay, let's recolor the mouse. I mean, we as humans know this is still a mouse. So in theory, our network should be able to tell the difference as well. Same if we rotate it, if we move it left to right, or if we scale it. These are still mice, fundamentally. So we can just shove these into our training data. And in theory, this should help the generalizability of our model. Now, data augmentation doesn't always work in practice. It's typically something that you like, you know, implement and see if it improves your validation error, which is a lot of things in machine learning. But it is something worth considering if you're worried about the size of your data set. And also your data is of a certain form where you can go like, hey, I should be able to do a pretty easy data augmentation. Like in the case of this mouse, it should be pretty easy to just shift it over. So it's something to keep in mind. All right. So like in some ways, data augmentation is a hyperparameter because we sort of dictate like what's a meaningful, acceptable data augmentation to do. Yeah, so the model will train on this. Any questions on this sort of process of data augmentation? Okay, good. All right, yeah, I suppose I already paused. Okay, so we're also gonna talk about improving learning performance. So this is like I don't know how to put it. This is like a process that was sort of motivated because we wanted our models to converge faster and to be more efficient when they converge to certain points. Like there are a lot of properties that we aren't exploiting with our vanilla gradient descent that we talked about all the way in our first machine learning lecture. And there are lots of things that you guys probably ran into that second lab, like your machine learning, like I'm sure you guys remember like that second question where it was like implement mini batch gradient descent and it helped your training loss converge to a much lower loss. You guys have any memory of this? This is like, technically speaking, mini batch gradient descent isn't like actually supposed to do that. It's a byproduct of the noise that mini batch gradient descent generates, which we sort of asked you guys about. But these tricks that we're about to discuss are much more robust ways to sort of improve your model converging on a good, like, local or ideally global loss minima. Okay, so if you remember, we had that whole lecture on backpropagation, right? And then we started with a gradient here, and then it moved back, and then it moved back, and then it moved back, right? If you remember gradient descent, you were taking a learning rate, multiplying it by the gradient, and subtracting it away from your weights and biases. If your gradients are really small, a lot of learning, like learning doesn't happen very well. So we're worried about our gradient sizes because we want our model to learn at all points in our neural network. So the process of backpropagation is basically saying we're taking this gradient, it's usually some strong value, and then we backpropagate it through the network. Now, what we're worried about is the upstream gradient will reach these gradients or reach these neurons, and then the local gradient that we derive here through backpropagation, right? It'll propagate through these, but the gradient could have shrunk. And if you imagine, if you have a very deep network, your gradient could shrink all the way back to the first layer. And if it does that, your first layer isn't going to learn. And that's a pretty big problem, because if you have basically zero gradient at your first layer, nothing's going to happen. And nothing's going to happen for a pretty long time. So yes, this is basically what I was saying. These gradients will sort of get lost as we move back further into the network. Okay, so this is the sigmoid activation function. I don't know if you remember this. This is one of the things that we sort of discussed as a activation function that you could use, but we sort of recommended that you guys use ReLU. This is one of the reasons why. If you notice, when we take the derivative of this function, or the gradient of this function, I suppose, here in this intermediary range, it's pretty good. It takes on like a pretty good finite value. It's non-zero. But you'll notice that the gradient saturates as our x changes to be very high or very low. That can be a problem, because if your x is consistently high, then you're never going to get any learning, because the gradient will basically be zero. So this is something we'd like to avoid. So this is why we motivated ReLU. And you might wonder, what about this section where it's negative? This will saturate as well. That's true. And people have developed different activation functions to sort of deal with this. But ReLU just sort of empirically works. So we sort of just took it and ran away with it. The important thing is it doesn't saturate in this positive region. So your gradient is preserved as long as it's positive, which is generally speaking a good thing. Okay, batch norm. We sort of mentioned this in the work session. If you went there, I had a whole long-winded spiel about batch norm, but we'll talk about it more formally here. So hopefully you guys remember from your statistics course, but we do something. We can take a z-score of a value. This is a thing that we do to calculate it. I don't know, what is it again? It's the p-value of the what chance this data point was observed if the distribution was normal or something like that. So taking this z-score is also a useful property in neural networks, because sometimes we want to pass in data to the network that's been normalized. So we'll get more into that, right? So if we have some denormalized data that we're passing into our into our neural network, and it looks something like this, right? The important thing is that our input features aren't constrained to any range. And if we have a bunch of inputs, like multi-dimensional input, those ranges can vary across those inputs massively. This means that same weights can produce really different results. This is not great. Yes, so this is a problem, because if we have constantly varying activations that come out of our neural network, or come out of a neural network's layer, we might affect our training negative. So let's consider a smaller scale example, not the massive dimensionality that our neural networks usually deal with. Let's consider something that has two weights and no bias. So a loss curve might look something like this, where we have the loss on the z-axis here, and then changing or tuning those weights will deplete along this sort of curve we have here. Okay. Let's say this is a topography graph. So when the lines are closer together, we observe a steeper slope. If we don't normalize the inputs, it might look something like this. So basically what this is saying is if we are moving in the W2 direction, we're going to see a really big change in loss. And if we're moving in the W1 direction, we're going to see, never mind. If we're moving in the W2 direction, we see a really big change in loss because the slope is much steeper. And if we move in the W1 direction, it's much shallower. That's not really consistent, and that's not really ideal. So something we show here is like, if you have like some sort of constant learning rate and you just sort of apply a traditional gradient descent, you can see how the greater changes in W2 will cause it to fluctuate and essentially not have good learning. We'd like our slope we'd like our gradient descent step to essentially just take us to the local minima. But because W2 varies so much, or because changes to W2 cause a loss function to vary so much, it might be difficult to sort of attain that. So let's say we normalize our data first by taking that z-score that you guys hopefully remember from your statistics class. So essentially we transform the data set by, normalizing it. Our loss function will look something more like this. So the loss curves will essentially be like, a unit step in the W1 direction is roughly equivalent to a unit step in the W2 direction. This is useful because you have to consider that we also set like one global learning rate that is irrespective of which weight we're calculating on. So generally speaking, we'll have a smoother convergence to the center because we're not fluctuating too greatly in some loss or in some axis that has steeper loss curves. Did that like make sense as far as why we motivate normalization? Okay, so this is basically like a much smoother convergence than what we saw before. And we talked about what we should do to normalize our data, which is to, I think I changed the order of this by accident. Yo. Is there no officer meeting?
It's done.
What? Okay. All right. So we were talking about normalizing our inputs to the model. We were talking about normalizing our data. Now, that distribution that we normalized, if we only normalize our input data as it was moving in, that distribution can change actually. Because essentially what happens at every neuron is we do a linear transformation of the data, and then we apply a nonlinearity. So we apply, the weights, the biases, and then we do a rate loop or some other activation function. That can drastically change the distribution because the weights that are applied to each input are different. So we'll have essentially an entirely different distribution, and that distribution isn't going to be normalized. So this is something that we were discussing at the work session, which is called internal covariate shift. And it's basically, covariate shift is basically like having different distributions of data within the same data set. That's called covariant shift. The reason why it's internal is that when we move into the network, it's internal. So we'd like to address internal covariate shift by essentially saying, hey, at each one of these layers, we should normalize it. That's basically the idea of batch normalization. So after we apply our weights and biases, we do a normalization. Here we note that it's right before the activation function. I think this is empirically determined to be better, but strictly speaking, I think we do this because it's ReLU. And ReLU has the, if you think about it, ReLU essentially will cause your data to denormalize because it cuts off everything at the halfway point, like negative. So we tend to do this before ReLU. Any questions about the why we're doing this? Okay. We have some variables here. You don't have to look at it too much. I think it's going to make sense if we go to here. Basically, the reason why we call this batch normalization is because the normalization is calculated over a batch, like a batch of training data. So essentially what this is saying is we calculate a batch mean for all the data that we're currently passing in. So this is the mean, and then we also calculate the variance. and then we just do a normalization. This epsilon here is simply just a term, so we don't do a divide by 0. You guys might remember doing that in the second lab with the sigmoid loss function. It's a similar motivation. So does this make sense, like this normalization process? Okay. And then the last thing we do is, let's say, okay, in this equation, what would, if we normalized by this, right? What would the mean of our new distribution be? 0, yeah. And then what would the variance be? Unit variance, yeah. So what if we wanted those to be different? So this motivates this next slide, which is basically saying, let's just multiply by a gamma and add a beta. And these can be learnable parameters. And as we train the model, it'll learn what the variance and what the mean of the distribution of what the distributions should be. And these are learnable parameters. These aren't hyperparameters. And basically in the math, you can calculate the gradients for these parameters and just apply them as you would with gradients. Question?
I'm just trying to understand this in relation to the smoothing of the gradients.
Right.
How does this like, I guess I don't completely understand how learning a different gamma and beta than just the unit, and like how that would help, how that would improve us beyond
just having the unit. Yeah. So that's a good question that I'm not entirely confident in the answer in. I think the choice was made just because of flexibility. Yeah. Like, you know, because these are learnable parameters, right? Yeah. If 0 mean and 0 or unit variance was like better for the situation, it would simply learn that.
Do you think it has something to do with like hyperparameters that we choose, like the learning rate might be better than something that's not there? Is that maybe a reasonable assumption to make?
Yeah, so I guess what you're saying is like, you know, perhaps a high variance corresponds with the gaps between these topography curves being longer or something like that. So our learning rate that we pick, like let's say we accidentally picked a really large learning rate, you know, the learned variance might cause the variation in or like the descent of this to be more, I don't know, like more robust for that particular loss curve. I could see that being the case, but I'm not entirely sure. I think because you're also in C147, like research on that. I think yeah, like because the history of batch normalization is it wasn't actually motivated by the smooth loss curves. It was actually motivated by the addressing of the covariate shift that we we're sort of talking about in the second part of this section. The smoothing of the loss curves was sort of just observed as a byproduct. And then people were arguing that that is perhaps why batch normalization tends to help. I'm not super qualified to speak on that, like whether internal covariate shift or the smoothing of the loss curves, which one's better, or like which one has more impact. Any other questions? Okay. We've been here. Okay. Let's power through the last part. Okay, so let's talk about optimizers. So we, at the very start, introduced gradient descent, which was a sort of foolproof method of saying, like, you know, if we can calculate our gradients, we simply use a learning rate, subtract away the gradient, and we know we're guaranteed to converge at least towards some sort of minimum. Now, it's very foolproof, but this sort of algorithm could use a lot of improvements. If we look at that example we had earlier before we were doing batch normalization and it having this sort of noisy behavior, we see that like as humans, we would intuitively sort of pick the slope that converges towards the local minimum much better. But in this case, this gradient descent algorithm can be pretty inefficient sometimes if our gradients just happen to be larger in this direction or something like that. So we sort of can use a lot of mathematical techniques like, I don't know if you guys remember from your statistics classes, but like first moment and second moment of like random variables and stuff like that. We can sort of throw those techniques at machine learning and gradient descent and try to improve gradient descent. So let's talk about one of the most intuitive ones, which is something called momentum. Okay, so let's consider this loss curve and these gradient steps. Something we sort of see is that, the gradient bounces between these two slopes that are pretty steep. And because the slopes are steep, we know from gradient descent that that's why it's doing that overshoot back and forth every single time. But wouldn't it be nice if we were sort of gathering some momentum as we were going down? And this momentum would push us in the plus x direction. So picture like this as being like the path of a ball. We see like intuitively from our understanding of mechanics and physics that the ball would gather some momentum towards this local minima. Does that sort of make sense from like a physics standpoint? Like why this might be intuitive? So we can implement that mathematically. And what we can do is we can keep a running average of our gradient steps and sort of append that to our gradient descent to make it move in a better direction. So, okay, let's take a look at what that means for a second. So this back and forth that we're having in between these gradient steps, in the plus y direction, what would that average out to be? Or in the y direction, sorry. What would the magnitude of that vector average out to be? Because it's moving back and forth. Yeah, 0. So if we kept a running average, our running average would only have a component pointing in the plus x direction. Because generally speaking, this, like, if you think of it as a ball, it garners momentum in that x direction, which is ideal. So why don't we just keep that running average and add it to our gradient descent? And that's sort of precisely what we do. So we keep a running gradient average, which we denote as v, which is basically momentum. And our alpha is still the learning rate. Or sorry. We have an alpha that weights the past gradient steps because we don't want like gradient steps from too long ago affecting our current one. So this alpha is basically applied sort of like recursively. You can think of like at this step, at the very last step, the step before it has one alpha applied to it, but the step before it has an alpha squared applied to it, and so on and so on. So it's sort of applied recursively in that sense. So essentially what it's saying is that the further away the steps, the less it matters. Epsilon is our learning rate, which we always had, and then we also have a current gradient. So our equation would end up looking like this. We update our momentum first by adding sort of like the current gradient, or sorry, this part is still our traditional gradient descent. We just sort of combine it in this momentum equation, but we basically update our momentum by saying, let's take our current momentum and update it with the previous momentum times our alpha. This is sort of that recursive step I was talking about alpha being applied like at higher power levels. And then we simply just add this vector to our gradient, or to our weights, and it's performing gradient descent as well, because this epsilon times gradient is just our learning rate times the gradient. And then we can sort of visualize this by saying, okay, we have a previous momentum component, we have our gradient component, which is just like perpendicular to this loss surface. Can you guys see my cursor all right? I just realized it might be tiny. Okay. I'm not sure how to address that. Like, I hope it's okay. But yeah, it's perpendicular to that slope there. So we know that that's our gradient step. And then the weight update will, generally speaking, move better towards the center of our loss function. Any questions on that? Okay. So our next sort of improvement to this algorithm is actually also pretty intuitive. So if you might imagine, right, if you have a ball rolling down a hill and you wanted it to stop at the bottom of the hill, if we were obeying normal physics and using momentum, the momentum would carry it past the local minima and then it'd roll down again. This is something that we observe in real life, right? So I don't know, you guys have had EE3, right? Like most of you guys remember PID control? What was like the term that sort of corrected like if you were moving too quickly towards like something and you wanted to slow it down before you reached it? Yeah, it was the derivative term. This is like roughly equivalent. Basically, Nesterov momentum, which is what this is called, is basically saying, let's let the momentum carry us past our point and then evaluate the gradient there. And that way, if the momentum was going to already carry us past the local minima, the gradient should point in the other direction. So they should cancel out. That's basically Nesterov momentum. Now, the equation might look somewhat complicated, but it's actually really easy to implement in practice. We don't have it here, but it does not necessitate computing a new gradient. So basically what this is saying is it's saying compute the gradient after we do the momentum component, which is what's sort of being depicted here. You do the momentum first, and then you compute the gradient. That's what it is like in theory, but in practice, fortunately, we don't actually have to calculate a new gradient. You can get away with this by storing the old values. Just like how you, hopefully you remember in PID, you didn't actually have to do a derivative. You just kept a running, you just kept like a running like last variable of the previous term. That's basically what I wanted to say here. Any questions on why we do this? Okay. All right. So we talked about momentum and stuff to do with momentum. That's sort of what we call like the first moment in physics, because, or sorry, in statistics, because this is like a first order. This is like a first order term. It'll get more clear when we look at what the next algorithm is, which is Adagrad. So Adagrad is basically saying something that we also somewhat find as intuitive, which is if you've moved far, you might imagine that you're closer to the local minimum. So your learning rate should be smaller. That is hopefully intuitive. So we might be like, okay, well, if we've moved far, let's just keep a running mean of our gradients weights like squared, or the L2. And then we sort of decrease our learning rate proportionally to how far we've moved. And we're sort of motivating that by saying, if we've moved far, we probably want to move less because we're probably closer to our local minima in this case. So that's basically what this is. It's also like the D term. All right, so the math here is sort of similar to what we were talking about, which is we're taking the second moment here. We keep the running mean of this, or it's not a running mean, it's a running accumulator in this case, of the Hadamard product of our vectors, which is basically just saying that we multiply them element-wise. So this is essentially just like an L2 norm without the square root, I think. But essentially, if we've taken big gradient steps, this will be big. If we haven't taken big gradient steps, this will be small. And we have our epsilon in the numerator here in our gradient step, and then we have this in the denominator. And essentially, can someone tell me what Greek letter this is? I've forgotten. Nu. Okay, thank you. Nu is also a corrective term for the avoiding the divide by zero. Okay, we take the square root sort of to deal with the fact that we haven't done quite exactly the L2 norm here. And essentially what this is saying is if our running mean is really big, we should have a less of learning rate to compensate for that. Any questions? Okay. All right. You might have noticed that in Adagrad previously, this alpha, it only has, or this A, like accumulator, it only gets bigger. Why might that be a problem?
You might get stuck in a bad part of the surface if you're learning these on it.
Yeah. So sometimes we want to escape a local minima. Like we have some motivation for doing so. Like if we just get stuck in like some local minima that is not actually particularly good in terms of loss, we'd want to move past it. And Adagrad would shrink our learning rate permanently. What we can do is we can just add this beta term and the 1 minus beta. I won't get too much into it here, but mathematically, this would ensure that A could in fact decrease because beta will be a term that is less than 1. So at worst, this is 0, and this beta is like some 0.99 or something like that, and then it will multiply the A and it will decrease by 1%. So this ensures that our learning rate doesn't permanently decrease. Make sense? All right. Now let's talk about like the brainchild of everything we've talked about, which is Adam. So Atom simply just combines RMS prop and momentum. You can see how both of these would be useful because they were sort of addressing similar, but like some ways different issues. So these are the equations. It's basically just a combination of everything we've done before. But there's also an extra term that we'll talk about here, which is bias correction. So essentially, all of these accumulators, you might imagine, get initialized to 0 in your first training iteration or your first gradient descent step. Now, that 0 is sort of like not a legitimate value. We just initialize it to be 1. So if we took one step right at the start, we might imagine that our true V and our true A are affected strongly by essentially what a bias is. Like essentially what is a bias, which is that we initialized it to 0. That's not optimal. So the other thing we keep track of in Atom beyond the momentums and the second moments is we also keep track of time. So this is simply a beta term to the power of t. This is essentially saying after a certain amount of iterations, this bias term will peter out and then it will continue as normal. What this equation is essentially saying is that beta is another term that is less than 1. When we take when t is very high, i.e. we've gone for a long time, it'll be 1/1 because this value will approach 0, which will be, essentially v to v. It'll be without its bias correction. But when t is low, i.e. 0, this will be some large number. So essentially what it's doing is it's weighting the original thing we set, like that original bias we had, much less than our current gradient or our current gradient square, our current first moment and our current second moment. This is pretty important to do, this bias correction step. But it is sort of just mathematical semantics. Any questions? Okay. So we're sort of at okay, these are all the equations. We're not going to ask you to implement this. You guys saw that you sort of just do TensorFlow dot loss dot or TensorFlow dot optima dot atom or something like that. So you don't have to implement these, but this is what it looked like. Okay, last thing. Anyone want to take a break or should we just get it over? Okay, all right, good to hear. Okay, last thing, binarization. So as you might imagine, neural networks can be pretty big. You guys hopefully have looked at Lab 5 and there was that list in your TensorFlow summary, which is number of trainable parameters or something like that. I don't know, it's getting to 4 million or something like that. Now, if you recall, we want to put this on a pi, so it wouldn't be great to stick all these parameters on. They can get very large. So we have a process called binarization, which is essentially this, right? This is a small network already, but we have to do 18 multiplications for all the weights, which can be computationally expensive when we scale this up, 14 additions, and 7 activation functions. So if we grow this network, that'll get pretty ridiculous pretty fast. So how can we deal with that, right? Now, I don't know, as per information theory, if we sort of decrease the amount of operations we do, we're always going to lose information. So this process of binarization is going to lose information. It's just a matter of what we're going to keep. So the bulk of the work is weight multiplications because multiplies between floating point numbers are pretty intensive. So since I want to note that since your weights will be stored as floating points, you're going to want to pass in data that's floating points as well. You sort of do the conversion. I don't know if you remember, but in Lab 5, we have you convert everything to a float before you put it in. This is why. So every single connected neuron is going to get a floating point multiplication, which is not great. So what can we do to essentially correct this? And what we're going to do is we're going to convert everything to a bit level, binarization, basically. So if we convert, okay, the important thing is this process of binarization, we do it on a trained network already. This is an important distinction because we're not going to train it when it's binary because that would be suboptimal. Essentially, you train it first and you binarize it. So your weight of 32 bits is just going to become 1 bit. And then your operations are going to be much more doable on a Raspberry Pi, pretty much. The process of binarizing is going to involve binarizing a weight, binarizing the activation, and then binarizing its multiplication. One of the things we can do to essentially binarize is just to use the sign function. So if we reduce a floating point number to just one bit while preserving useful information, we usually just use a sign. What this means is our activation for every neuron is going to be the sign function. Now, this is why I mentioned that part about we're passing a trained network to this first. We talked about how gradients will saturate when our activation function is flat, because when it passes through, it's just going to be a gradient of 0. If you notice, everywhere where this function is differentiable, the gradient is going to be 0. So this would be terrible to train with, which is why we pass in the trained network first. So this is important. Don't train with this activation function, please. Our weights will also go through the same thing, which is just we're going to take the sign function of the weights we trained as well. And lastly, we just do binary multiplication with what operation? Anyone remember? Like M51A, people who are in DAV, M16.
Sorry.
Yeah, sorry. So that'll do things much faster. Yes.
How much will this reduce performance of the network?
So, yeah, that'll depend a lot. As you might imagine, networks might respond to that differently. There's research that suggests that if your network's trained well, it's not too significant. For our purposes, if we were to shove a neural network on a Pi, it's pointless to have perfect accuracy if the model can't do real-time inference. So it isn't so much that you'd make this choice out of preserving accuracy, I suppose. But I imagine you would be able to lose a lot of accuracy. Ideally not.
If the network's really big, I would imagine that the loss might be a little lower too, right? You know, as you scale the network, it wouldn't matter as much because you have more weights if you're dealing with.
The loss increases, or at least error increases as you backpropagate through more layers, I think.
Well, you won't be running back propagation on a binarized neural network because you won't be training it anymore. You pass in the trained one and you only run inference is the idea. As for how your accuracies, like how badly your accuracies drop, I think that's something that you could only really just evaluate on a per network basis.
Could you consider streaming from?
Oh, like some other source? Yeah, there's a lot of ways that we can consider it. I mean, you've seen through SSH how slow the Wi-Fi can be. So, but in theory, you are only passing 2 PWM signals with the schema that we sort of have. So it could be possible. The problem is, you know, we have this curriculum where we teach you guys a lot of things conceptually, and you know, we might just to do that, we might hand you like software to have already done it, but you might not truly understand it. So in terms of like the project, that is definitely something to consider, but it would be somewhat possibly annoying to teach all the extra Raspberry Pi stuff involved. Okay, that is it. Any questions about anything? Okay, how do I stop you?